Good day, everyone. This is Professor Friday coming at you one more time. Today we're going to be solving some non-homogeneous second-order differential equations. So the one that I've got for us today is we are going to solve the non-homogeneous differential equation y double prime minus 4y prime plus 3y is equal to 10x e to the 3x power. Now, first thing you're going to want to do anytime you're taking a look at a differential equation like this one is just sort of recognize what you have. So first thing I'm going to do is over on the left hand side we'll identify this as being second order due to the fact that the highest order derivative we see is the y double prime. I see that we have constant coefficients, which means that we will be able to use the technique of either annihilators or variation of parameters. And then over on the right hand side I see that this is not equal to 0, which allows us to identify it as non-homogeneous. So again, because these are constant coefficients, for a non-homogeneous problem that means that we'll be able to use the technique of either variation of parameters or the method of undetermined coefficients with annihilators. So first thing I'd like to do is set us up for success in both of those by talking about the associated homogeneous equation, which would be y double prime minus 4y prime plus 3y is equal to 0. Now I'm going to throw in some polynomial differential operators. So d squared y minus 4dy plus 3y is equal to 0. Factoring out the y gives us d squared minus 4d plus 3y is equal to 0. So with that in mind, we can factor this polynomial differential operator and then figure out what we have in terms of annihilators. So when we factor, I see a d minus 3 and a d minus 1. The functions that are annihilated by these two things would be e to the 3x and e to the 1x. So I'm just going to refer to that as e to the x. So our fundamental solution set is going to be the set containing these two functions, e to the 3x and e to the x. And that also allows us to express our complementary solution, which is going to be a linear combination of these two functions. We'll use y sub c for the complementary solution. This will be c1 e to the 3x plus c2 e to the x. So that takes care of our associated homogeneous equation and also sets us up for success for either variation of parameters or method of undetermined coefficients. I think today we're going to use annihilators and the method of undetermined coefficients. So with that in mind, let's head back to the original differential equation that is already in its factored form. Already got the annihilators going on. So with that in mind, for the method of undetermined coefficients, the question that you get to ask yourself as part of this process is, what annihilates this? Now, when I take a look at that, I see that the root here, or the base of this, is an exponential. It's e to the 3x. But I see it also has an additional coefficient of x associated with it. So, for the e to the 3x, we will see a d minus 3. Because of the additional coefficient of x here, we're going to need to square this. If you do have a power of x, then the exponent that you'll need on your annihilator is always going to be 1 higher than the power of x that you see. So if there's no x, you use a first power. If there's an x to the first power, we would go squared. If there were an x, to the 37th power, we would need a 38th power. But I'm pretty sure you're protected under your Eighth Amendment rights on that one to cruel and unusual punishment. So with that in mind, our next step is going to be head back up here and apply this annihilator to both sides. So we're going to apply a d minus 3 squared to both sides. Just about out of room on this sheet of paper, so we're going to switch over to the next sheet, and I'm going to recopy what I just had written down. We had just applied a d minus 3 squared to something that was already factored as d minus 3 and d minus 1, y. And then we also applied a d minus 3 squared to the thing that we had on the right-hand side, 10x e to the 3x. Now the purpose behind doing that is that over on the right-hand side, this annihilator will, well, it will annihilate this function. To annihilate a function is to turn it into 0. On the left-hand side, if we group our factors together, we're going to wind up with a d minus 3 quantity squared, quantity cubed, and a d minus 1 applied to y. Now, what we're looking at is yet another homogeneous equation. So with that in mind, this is going to contribute a total of 3 linearly independent solutions. Those would be e to the 3x, x e to the 3x, and x squared e to the 3x. The d minus 1 will contribute 1 linearly independent solution, and that'll be e to the x. Now, a linear combination of all of these would create the general solution of this homogeneous equation. The issue is we're not finding the solution of a general homogeneous equation. We actually created a homogeneous equation out of this. We already know what is contributing to our complementary solution, and that was these two guys right here, the e to the 3x and the e to the x. Everything else is going to be associated with the particular solution. The reason we call it, though, the method of undetermined coefficients is because this is part of the particular solution, we actually solve for all of the coefficients of our linearly independent solutions. So what this creates for us is what we call a trial solution. The trial solution is going to be comprised of x e to the 3x as well as x squared e to the 3x. X squared e to the 3x. However, these are going to have coefficients that we're actually going to find. So instead of calling them c's, I'm going to give them different names. I'm going to call them a1 and a2. So we now have a new goal. We're going to solve for a1 and a2. If we can solve for those two coefficients using the method of undetermined coefficients, then we will have our particular solution. Now the way that we find these two things is what we're going to do is take our trial solution and plug it back into the original differential equation. The original differential equation being what we started with in this whole process. Because it was a second order differential equation, I'm going to take two derivatives of our trial solution and then plug it back into the original differential equation. So trial solution prime. Looks like we're going to need the product rule a couple times in here, so I'm going to do a little something to potentially help us out. I'm going to factor an e to the 3x out of this big expression before we differentiate, and we'll see if this helps us out. That way we can apply the product rule. First times derivative of the second, so that'll be a1 plus 2a2x plus the second times the derivative of the first. That'll be 3e to the 3x. Then I'm going to do the same sort of factoring thing that I just did and leave the e to the 3x out front. As far as constant terms are concerned, it looks like the only constant term we're going to have will be a1. As far as an x term is concerned, I see 2a2 as well as 3a1. 2a2 plus 3a1. And then as far as an x squared term is concerned, looks like we'll have a 3a2. 3a2 x squared. So that will be our first derivative of the trial solution. We'll also need a second derivative. So once again, we'll go first times derivative of the second. Derivative of the second, constant goes to 0. Something times x becomes just that coefficient, 2a2 plus 3a1. And then we'll get an x squared in here as well, so that'll be 6a2x. Plus second times derivative of the first, that'll be a1 plus 2 2a2 plus 3a1 times x. Oh boy. Let's see if this all fits. Oh shoot, I wasn't supposed to do that yet. Plus 3a2x squared times 3e to the 3x. Totally made it work. Not very well, but you know, it's all there. Then for funsies, let's go ahead and do that thing that I just did, and we'll do it again. We'll factor out the e to the 3x. Oh boy. Let's see how many regrets I have after this. Constant terms, we're going to have a 2a2 plus 3a1 plus 3a1. So 2a2 plus 6a1 plus. For x terms we'll have a 6a2 here. We'll also have a 3 times 2a2. That's an additional 6a2, so 12a2 plus 3 times 3 times a1. So plus 9a1 x. And then for the x squared term, we'll have just this guy, which will be a 9a2 x squared. My goodness, that just is so exciting. So now I'm going to take our second derivative, our first derivative, and our original trial solution, plug it back into the original differential equation, and then set it equal to the 10x e to the 3x. I think I am ready for a fresh sheet. So we're going to do y trial double prime minus 4y trial prime plus 3y trial. That all is going to be equal to 10x e to the 3x. Now I'm going to be borrowing the derivatives of the trial solution from the previous page. If you need to rewind, please feel free to do so as I'm copying these down. So the second derivative of the trial solution, I'm going to be doing a lot of looking back and forth for this. E to the 3x times 2a2 plus 6a1 plus, we'll have 12a2x plus 9a1x plus 9a2x squared. Minus 4 times the first derivative, which was e to the 3x times, oh boy, so we had an a1 plus 2a2x plus 3a1x plus 3a2x squared plus 3 times the original function. I'll just go ahead and factor out the e to the 3x from that as well, just for the sake of consistency. We'll have an a1x plus a2x squared. This all is equal to what we had on the right-hand side, 10x e to the 3x. So part of the nightmarish part of this process is actually keeping track of everything. So what I'd like to do first and foremost is divide both sides by e to the 3x. So essentially what I'm going to do is take out that, and that. Then I'm just going to sort of recopy everything into groups where we'll have the constant terms together, we'll have the x terms together, and we'll have the x squared terms together. So little arrow right here. As far as constant terms go, from the first group we had these, so 2a2 plus 6a1. From the second group we had just the one constant term, so that'll be minus 4a1. And then from the third group we had no constant terms, so the constant terms are done. Plus x times, we'll group all of the x terms together. From the first group we had 12a2 plus 9a1. From the second group we have a coefficient of minus 4, so that'll be minus 8a2. And then minus 12a1. And that's it for that group. Then as far as x squareds are concerned, from the first group we had 9a2. From the second group, we would have minus 4 times 3a2, so that'll be minus 12a2. And then for the last one, oh, I think I missed an x term back here. Oh boy. Plus 3a1. Hopefully that winds up being ridiculously convenient. Plus 9 minus 12 plus 3. Oh yeah, that's ridiculously convenient. Plus 3a2 for the x squared term. And again, this is all still equal to 10x. One really great observation, well, a couple really great observations that we can make here. 9 minus 12 plus 3, all a2s, those are all 0. And then back, when I was busy screwing this up, 9 minus 12 plus 3, those will be equal to 0 as well. So that is some good news. Little arrow, and we'll recopy this one more time. As far as the constant terms are concerned, we have a 2a2, and when we combine these like terms together, we'll have a 2a1. So 2a1 plus 2a2, that's our constant term. Plus x times, we were able to get the a1s to cancel out here, so we'll have 12a2 minus 8a2. That'll be 4a2. This all is equal to 10x. But I'm going to rewrite this in a slightly different fashion. Over here, this is a constant term plus x times a coefficient. I'm going to write the right-hand side exactly the same way. Constant term plus x times a coefficient. What this allows you to do is it allows you to set up a system of equations. For the coefficients of x, this tells me that the coefficient of 4a2 is equal to the coefficient of 10. The constant term of 2a1 plus 2a2 has to match the constant term on the right-hand side, which is 0. The first equation tells me that a2 is going to be equal to 5/2. The second equation tells me that a1 is simply going to be the negative of a2. So a1 will be negative 5/2. Reinterpreting what a2 and a1 were in the first place, we go back to our trial solution. The trial solution told me that a1 is the coefficient of x e to the 3x, and a2 is the coefficient of x squared e to the 3x. So a1 times x e to the 3x plus a2 times x squared e to the 3x. This is your particular solution. Put some stars around that because, well, it's a celebration. Your general solution is going to be your complementary solution plus your particular solution. Complementary plus particular. I think that we can make this fit on this sheet. Oh yeah, we got plenty of room. So complementary solution was c1 e to the 3x plus c2 e to the x. The particular solution, since I've already screwed up and written that down as a plus sign, we'll do the a2 term first, and then minus 5/2 x e to the 3x. The order in which you write the terms is not horribly important. What is important is that they are all there. So, hope you enjoyed this one. Plenty more to come over the course of the weekend. So, have a great day.